So now that we have already know what a relational model is, and we already have the definition of a dependency and the relation, the tuples, attribute, and the functional dependency, we also know the data type and primary key definitions. Let's start to see how we can physically implement a relational database. So we see this slide before. Relation can be easily expressed as a two-dimensional table because relations consist of tuples. All tuples in the relation have the same attribute in the same order. So it's easy for a relation for us to draw a two-dimensional table to express how a relation looks like. This makes it very easy to define data set. And this is part of a reason why relational database is so popular, because it's very easy to implement, right? Each data set can be represented with a series of relations. This is what basically what the research of DataCode showed, that each data set can be represented with a series of relations. And each relation is a two-dimensional table. And note this here, when we say table here, is a conceptual table. It's something that you have like X by M by N matrix of data, not a database table that we will discuss in a minute. But this is the relation. When you try to implement this relational model into a database, you will organize your data into a series of database tables. Each table corresponds to one relation, because your model, basically, relational model is a series of relations. You are just mapping each relation to a table. So you will then store those tables one by one, each stored as a two-dimensional table. And from now on, when we say table, it's always database table, unless I specifically mention. Database that is based on relational model is called a relational model. It's called a relational database. And DBMS for relational database, the database management system for relational database is called a RDBMS, the Relational Database Management System. And how do you create a relational database? Then it becomes apparent that it is a two-step process. You will have a conceptual logical design where you will create a relational model. The official words of that is through a systematic process of database modeling, we map real-world questions into a logical model which contains a collection of relations. This collection of relation, the result of it is a collection of relation, and this is called a logical model. And then once you have a logical model, you can map each relation into a database table. This result is a series of database table definition. This is called a physical design, and the result is called a physical model. So just a picture to help you better understand. From real world, we map real world data set into a series of relations. And thus we form a relational model. Then we map this relational model to a database. You are basically introducing a mathematical layer between real world problem and the computer implementation. So each relation represent a real world thing. How we map that, we will cover this later. But basically at this point, we will consider each relation as something in the real world. And each tuple represents a real world instance of that thing. And each attribute, of course, represents a characteristic of that instance. Mapping this thing, instance characteristics into relation tuple attribute is called logical modeling. So when you try to define a relation, you define a relation by describing the attribute of a relation. How many attributes does a relation have? What are they? What data type are they? And in which order they are listed for that relation? This is how you describe the attributes of a relation, and this is how you define a relation. But once you have a relation defined, you know what attribute you should see in any tuple and the order. You will populate a relation by inserting tuples into this relation. Basically, you will map for each real-world instance, you will map the characteristics of that instance into the attribute of that tuple. Then put this tuple into a relation. This is populating the relation. So for example, we've seen this before. We have the relation of course. So how do we define a course? Let's say we pick up a course like DS530, and we identify what attribute it has, what characteristics does it have. How does DS530 different from other course? What makes it unique? It's the course code, DS530. It's a course name and the course credit and the course time that make it different from other courses that this course entity, this course relation has. And these are the attributes that we identify as a part of this course, of this tuple, right? Of this relation. So all tuples in the relation will have the same attribute. You need to check, make sure all courses have these attributes: code, name, credit, time. Apparently, we all know they do. All tuples in that relation, in the course relation, have these attributes, and we can arrange them in the same order. Each attribute, of course, also has its own data type. Then this will be a part of the attribute definition or relation definition. Then once we define a relation, this relation as the combination of a course, code, name, credit, time, and each of attribute have a data type, we will create tuples based on this definition. For DS530, we will define the code as DS530. The name will be big data and data management, and credit is 3, and time is Wednesday 6 to 10. So these are the things that you will be using. These are the way you define a relational model. You identify a relation, you define, you determine what attribute it contains, and also the attribute characteristics. Then once you define the relation, you will insert tuples into it. Relational model, once you define, can be systematically converted to a database, physical database implementation. The way you do it, as we said, mapping a relations into table. Each table will be representing a relation. Then each row will represent a tuple, which is a real world instance. And then each column represents an attribute. So here, similar to what we see in logical mapping, when you define a table, you define a table by describing the columns of the table. What's the name? What's the order? What is the data type of each column? So you define the column, and then you populate the column. You will insert a row into the table. It's basically a two-dimensional table. You have rows and columns. Each row is a tuple. Each column is an attribute. So you define a table by describing what columns should be in that table. And these columns will be the attribute of a relation. Then you populate the table by inserting one row at a time. Each row is a tuple. So from now on, you will see a lot of synonyms describing the same thing from different aspects. So mathematically, we have a relation, which is a conceptual model, a table in the logical model. And in physical implementation, it will be a database table. So in the future, when we say relation, it could mean anything from a relation or a table. Even when I teach you SQL, where you will strictly dealing with database tables, sometimes I may call it a relation too. So just so that you know, this can come. When I say relation, you need to have the good sense that it may be referring to a table, or maybe some other database objects that I'm going to teach you in this course, like views or subquery. So when you're dealing with the physical table, you insert a row, or sometimes it's called a record. And we sometimes may use the same word like instance or tuple to reference a row. When you run the SQL insert, I may say, oh, we insert an instance into a table. This is also a synonym that we are going to use interchangeably. Similarly, attribute can be called a column or called a field. You will hear me calling them columns, fields, or attributes. Okay, so now that we have been going through the relational model, we talked about how you create a relational model and how this how you create a conceptual design, logical mapping, and map them into physical mapping, physical database. Why this is important? Because relational model can be created systematically, consistently, and logically. And these three are three different aspects of this model. You can systematically do that, which means you can, it's easy for other people to do it without mistakes. And you can do that consistently. Different people may have a slightly different database to be designed, but the fundamental idea is the same. So you have a mathematical theory behind it. You have a relational algebra behind it. It's less likely to make mistakes and easy to prove that it's working. And also we see how simple it is to develop and implement. You are splitting the complex question of mapping real world question into a computer model. You are resolving that by splitting this into two steps. The first step is to create a relational model, a mathematical model. Then you map the relational model, the mathematical model into a physical implementation. This makes things much easier This makes the computer system much easier to develop and implement. And because you have a theory behind it, the result can be consistent across different platforms. So when you have the same SQL, you can run this SQL 99%, 95% of the time. You can run the same SQL across different database platforms. And most likely, you are going to get consistent result. It may not always be the same, but at least it's consistent. We will talk about this SQL compatibility later when we teach more. But at least at this point, I'm telling you, SQL can be consistent in results across multiple platforms with some maybe 5% of the exceptions. And then because we have this relational model and it says all the real world data set can be mapped into a series of relations. That means this model can be applied to almost all business scenarios. So this is why relational model is so important.